Hi, this is AP Calculus, section 6.1, slope fields and differential equations. You can warm up with this one. You want to use logarithmic differentiation to do that, and then I'm going to talk about slope fields for a little while and have you do the papers that we have given you from Nancy Stevenson. So why don't you try to warm up with this, and then I'll come back and then I'll talk about slope fields. So what you do with this one, logarithmic differentiation, you take the natural log of both sides. So you put a natural log here and you put a natural log here. And when I do that, I can take the exponent down, use that plug rule. So I have ln of y is equal to ln x times ln x. So how do we do this? Well, this is a product rule, and there's probably different ways to do that too, but we do this implicitly. So we go 1 over y dy dx, and then I take the first times the derivative of the second, which will give me this, plus the second times the derivative of the first, which gives me the same thing. So there's just two of those. So I get 2 ln x over x. Then I multiply both sides by y. When I do that, I use my original y back in. This is the function in terms of x. So instead of y, writing y here, I write x to the ln x. So this is the answer that you should get. Now, slope fields shows us derivatives at particular points. And so what we want to do is we want to go to your sheets that we have that deal with the slope fields. And here are some examples here. Now, what is a slope field? Well, what a slope field does is it gives us a picture of what kind of slopes we have at particular points. Now, we don't necessarily know what the equation is at those points, but we can tell you what the slope is because we know the derivative. And this has come up with technology and different things, but let's go through this example here and try this. So with this differential equation, this will tell us the slope at any particular point. So if I set up a t-chart, x, and it really doesn't matter what y is because our derivative is not defined in terms of y, but I set up x, y, and dy dx. And after a while, you can maybe do some of this in your head, but we'll start off like this. Now, with these items, I want to take a particular point. So for instance, if I take 1, 1, I want to find my slope. Since this is just in terms of x, I take the 1 and plug it in here, and I'm going to get 2 for dy dx. So that tells me that I have a slope of 2 at the point 1, 1. And so a slope of 2 is somewhat like that. Remember that if you have a slope of 1, it's going to be at a 45. Slope of 2, it's going to be a little bit steeper. 3, 4, 5, 6, more steep. And then if we have a slope of 1/2, then rise over run is going to be 1 over 2. That might not be, that's not too bad. And then if we have a slope of 0, that's going to be horizontal. If it's negative, then the slope will be down to the right. So what's going to happen is that on my curve here, and with my technology I can't do this, but at the point 1, 1, then I draw just a little segment right here, go ahead and do that, of a slope of 2. Now if I take another point, how about if I take 1, 0? If you notice, I still have a slope of 2. So at the point 1, 0, that's my x and y that I have here, I'm going to draw a line with a slope of 2. Now don't make these lines too long and don't make them too short. They have to be long enough so you can see the slope, but not too long so they run into the other ones. Now if I take and I do some more points, for instance 0, 0. Now with 0, 0, I'm going to have a slope of, take 0 plus 1, I get 1. So this would have a slope of 1 right here. So I draw that in. And then if I continue on doing this, I can do it for all the points. If you notice in terms of x, if it's all in terms of x, what happens when your x is 1? Well, my slope's always going to be 2. So in this row going down, my slope will always be the same. So draw some of these out, and maybe I can do one more. How about if I do -3 and then 1? At -3, 1, the x is -3, and so I get a slope of -2. Slope of -2 would be down to the right and a little bit more than 1. If you needed to use a straight edge, go ahead. Now what's the difference with this one? Well, this one's defined just in terms of y. So I'll do a quick point here. If this point is 1, 0, that means my y coordinate is 0, so my slope would be 0. So it's like this. I didn't do this one too. If m is undefined, the slope's undefined, that usually means a vertical line. So you get something like that. So go ahead and try these and figure out what some of these look like, and realize that there are some different patterns that we will have with these. And then I'll have to get a key for you in class. Now we're going to be dealing with the second part of this, which is dealing with differential equations. We've done differential equations before, and we see them like in this form. So if we have to find the general solution, we do dy is equal to 6 sine of x plus 4x. And what we want to do with this is that we need to multiply this by dx. And then I want to go ahead and take the integral of both sides. So the antiderivative of 1 dy is y. And then the antiderivative of sine is cosine, and it's going to be negative, plus 2x squared, and then plus c. So this is what we would call the general solution. General because we have the plus c. Now if I give you a fixed point on there, then I can find the particular solution. So in other words, I'm just finding what c is. So at 0, we have a y value of 5. So 5 is equal to 6 sine of 0 plus 4 times 0. My computer is just not liking me right now. Okay, so if we do this, sine of 0 is 0, so then I get my plus c. C is equal to 5. It won't always turn out to be that case, but in this one, we do end up with that. Oh, I'm sorry, I did that. I had to plug into the original y function, not the differential. So we have this, we plug this in, 0, and we get a c, and this would be negative 6. Add it over, c is equal to 11. So here's my particular solution that passes through this point here. Okay, now what will happen is that you'll see differential equations that take on a different form. So this will be kind of new for you. You'll see this form, y double prime minus y is equal to 0, and then this one and this one. What this means is that, and actually in college you can take a course that's called differential equations, and you deal with a lot of these things and make sure that we satisfy these equations. And so that's what we're going to be doing, is that we take, for instance, this y equals, and make sure that it satisfies this equation here. Now in order to do that, I need to find y prime, and I need to find y. So I have y, that's no problem, so I'm going to be plugging that in. But I need to find y prime. So if I do y prime, that's equal to negative e to the negative x. Now what I have to do is I have to put this into this equation and the y and figure out if this is equivalent. So I'm going to go and just do a replacement. Y prime is negative e to the negative x. And then y is e to the negative x. And does that equal, and this is what we kind of want to ask, does that equal e to the negative x? And sure enough, this is negative 3, this is 1, so this is e to the negative x equals e to the negative x. So this is verified. Okay, moving on to this last problem. I have this all written out just to try to keep this straight, but you got to try to follow this as best as possible. So I'm going to give you the y equals in this form right here. And so this is the equation I'm giving you, and I want to show that it satisfies this differential equation. So I have to find the second derivative, add 2 times the first derivative, and add 2 times the original, and show that it's equal to 0. So I have to find this second derivative and this first derivative. We're also going to do some substitution to make this thing work. So if I take the first derivative, I have to take this piece right here in red. So it's going to be the first, which is this whole thing, times the derivative second. So that's what I get here. Plus the second times the derivative first. And so then the negative comes out here. This negative came from the sine of x. That's all from this red piece. Then I take the derivative of this piece, which would be, once again, the first times the derivative of the second, which I get right here. And then the second times the derivative of the first, which I get right here. Now, if you look at this, this is the opposite of y, part 1. So that's the opposite of this thing right here. And if you look at this part right here, this is the opposite of y, part 2, which is the opposite of this. So if I put this piece with this piece, overall, I'm just going to get simply minus y. So this is both parts of minus y. So I put that in there, which might make it easier, might not. So now let's see. This is first derivative. Now I need to find the second derivative. So once again, I do the product rule. And so this is this one, first times derivative of the second, plus second times derivative of the first. This one as well. And you should be writing this down, pausing as you go. Now, what's the derivative of y? Well, the derivative of y is y prime. So I put this on the end. So this one right here goes to this one. The red goes to the red. The black goes to the black. Okay? Now, if you look at this, once again, this is the opposite of y, part 1, and this is the opposite of y, part 2. So I can just call this piece minus y. And then I have this minus y prime here. So I get minus y and minus y prime here. So this y prime, right there. Minus y, right there. So now here comes another tricky part. So what happens is that when I take this second derivative and I have it in this form, minus y and minus y prime from above, this one right here looks very similar to y prime. However, this sign and this sign are opposite. So you might call it the opposite of y prime, but then I got to deal with this one right here as well. So what happens really is that the opposite of y prime would be positive, negative, positive. So what happens is that I have an extra y in this thing from this y prime, so I need to actually take out this y. So this piece right here is equivalent to minus y prime minus y. So if I put this all together, this whole statement up here, I get y double prime is equal to negative y prime minus y minus y minus y prime. And that all comes from right here. And then I could simplify this, and then that's the equation that I want. So that satisfies it. Now, this gets a little nasty, but this is what happens for engineers. If you take engineering courses, you're going to be dealing with a lot of this e to the negative x cosine sine. And so you got to get used to it a little bit. This would be kind of an extreme example, but overall, I think you should be able to recognize it and see what's going on there. All right, so finish up some of that beginning slope field stuff, and then go ahead and do this assignment for section 6.1. Thanks, and have a great day.